All right, who's under the gun today? Excited? All right, what chapter are we on? DEs with more than one random variable. 2 plus. That's not even real. I hope not. What do you mean on campus?
No, everybody else is not here.
Oh yeah.
But I got extended to.
See, what are we? 6? Yeah. 7. Any questions before we get started? Yeah. Class, hopefully. Canvas. I hope.
Everything we're going to do 5.2
For the pair thing?
and
I want the pair program for.
Oh yeah. I guess so. I don't realize that. I don't know what it is. Probably. That's what it seems like. I guess we'll find out. Guess we'll find out. Sometimes, I have really good intentions and they don't work out. I like lay things out perfectly and then they are broken. So we're gonna double check. We'll find out. Did you look at it already? Does it have to do with derivatives? Okay, all right. As long as you kind of look through it, you're like, this seems mostly relevant, then it'll probably be relevant. Most of the time, previous Mateo did a good job. Sometimes not so much, you know? All right. Any other questions before we get started? Do you want to share starting off or do you want to go through the text first?
to the text because I only did for the example.
Okay, let's just do this then. All right. Take it away.
The chapter is about differential equations with more than one variable. That's it right there. And we're told that we can we can have as many variables as we want. So I think if I remember, we can only have one independent variable. We can all the other variables can depend on each other, but we need to have at least one independent variable. And through those equations are what we're going to be using in the example, but those are just to show that you can have derivatives that are dependent on two variables, but the dy dt I think it can have both x and y, but it's only has one independent variable. And here it's explaining how would we show that in the code that we have been doing, and it through there is showing you a notation that we in that we kind of know based on the ones that the differential equations that we've been doing in the last, from the last chapter and how we were trying to code through that. And here it is showing that through, with that, we can have a general form of, to represent both of those equations into one. And in this case, they use R, so f of RT. And below that, it shows that where R is your X variable, your Y variable, it can be as many variables as you want. And in that case, it would be f of RT would be f of X, XT, f of Y, YT, and it would just keep going for each variable.
Okay, let's pause for a second there. Does it make sense what we're doing here? Does it have to be spatial coordinates, X and Y? No. What other things can we put in here?
Spherical cylindrical.
Those are still spatial coordinates. Those are still spatial coordinates. Are those not X's? X of Y? I'm asking, does it have to be always space here? Can you think of any other types of variables?
I think of like counting macros, like protein, carbs, and fats.
Ah, okay. So this could be used more generally, right? So you could say, well, all of those depend maybe on the size of the person eating, and maybe they're all dependent on mass, right? And then you have specific things about it, chemicals, right? Anything else? Does the computer know that they are lengths? No, computer doesn't give a shit, right? So as long as we do the appropriate approximations, and we treat them properly, the computer will treat it exactly the same, right? Okay, and we'll see why this structure is so powerful quite shortly. Go ahead.
And so below, it shows us how do we, using the Euler method and the Runge-Kutta method, how do we incorporate that arbitrary variable R, that function R, into the methods that we have already used. And through that, so it basically shows almost pretty much nothing changes, except that now you use R instead of like X or Y or any of your variables that you have.
Good.
And then I think it's moving down now to the example.
I can give you the screen.
So in the example 8.5, it was using the equations that it showed in page 343. Those two that we are seeing, it's basically telling us, okay, we're gonna use those equations and we're gonna plot them so in the same way that we've done with the other with the differential equations that we did earlier, and showing how we can incorporate it into our code. So obviously, we initialize everything, and we define our variables. I use R as they did before. But do keep in mind that R is an arbitrary variable that we can use. You can define it as anything as long as the rest of the code uses that same variable. And here we define X and Y as the 0th and first element, respectively, of an array. We'll get to that. F of X, we write out F of X and our F of Y equations. And we put those into an array, into a float array. And then here is how we define, obviously, our start and our end. our start was in the example 0 to 10 seconds, I think. N is gonna be also our number of steps, our step size. And here we have basically the same that we've been doing for our differential equations. And here is the array that we had referred to in the user-defined function. The array here is, so it's basically telling us that at the 0th element, this would be our X, and our Y element is this first element. And then, just as we've done with our other differential equations, where we've done a for loop, we amend we add into our lists the value of X and Y respectively. And we do that through our fourth orders of Runge-Kutta, using the respective R to make sure that we are doing it through both X and Y. And then afterward, we add, obviously, just so we, from our Runge-Kutta method that we've done. And so after plotting both, you have, you've calculated both of them, both variables, in a lot less time than if you would have done it both separately. If I remember, when I was typing this all out, what stood out to me was, what I was trying to understand was, what it's basically trying to say is that for an X value in the array, go through all the steps, and then append to that list the new value of X, and keep doing that also for Y, until you finished all the steps that you need or that you inputted. And afterward, you have the list of all your values, and you grab it.
Any questions about this example?
Kind of confused on why we set R as an array by itself. Like, is that just like the initials for X and Y is 1?
Yes, those are initial values. So right here we have an array starting off. Like, this is a separate array from this array, because this array is going to be our values of X, or of X and Y. And then this array is going to be our outputs from the equations.
Okay. Thank you.
Anything else?
So when you're defining X and Y as R the 0th and R the 1st, that doesn't conflict with defining the array of R later on? Wouldn't you have to do that beforehand, or is that fine?
As long as we define R and don't leave it empty, then this should be.
Oh, okay.
So the interesting thing about this, everything that exists in here only lives here. So this thing R exists because the computer is told that it will exist. And the computer doesn't know that R exists, but because you tell it that there are 2 elements that you'll use, then it knows that I'm going to be given something that has 2 elements. And regardless of whether or not you pass it something called R, you could pass it something called Bloink, right? As long as Bloink has 2 places, it won't get upset. But if Bloink has 1 place, right? It is a list, but it only has 1 element. It'll say, this one's fine. And this one, it'll say, Bloink is expected to have a 2nd element, but doesn't. And then it'll give you an error. Does that make sense? So you can call it whatever you want. And I often encourage folks, I mean, this is taken from the example, right? So I encourage folks, just write this out as the word function or something so you don't confuse yourself. And then you can call this whatever you want. You can call this R. You could call this, input. Don't really call it input because input's important in math, but return. You can call this array, or you can put this on the line right above and you can call it the stuff that I'm putting out, and then you can return stuff that I'm putting out, right? Just so you can see the break.
What is, I forget, what is F of X of X of X of Y?
On page 343, you will, or I think in the textbook, that should be the two equations that we saw at the very beginning. That we need. The page before that.
Right. Yeah. But all I'm saying is here's where they first say it, right? So here's f of x. That's the first time they write it. And that is the derivative with respect to x, right? So now if we go back to the example, we go up here to the example, dx dt. And so f of x is just this thing here. Yeah.
So the solution to dy dt, for example, y equals, that's not gonna have an x, right?
Why not?
Because x is its own, right?
So, sorry, hold on.
How can you differentiate an independent variable with respect to a variable?
You can't. You can't. I can't. But computer can. Right? The computer's not doing the differential. Right? The computer is approximating the differential based on true values. So at a specific time, x is equal to 2 and y is equal to 1. So the derivative at that exact moment is 2 times 1 minus 2 is 0. And at that exact moment, f of y is 1 minus 2, which is minus 1, plus whatever this value is, right? And is non-zero. Do you see? So at every moment, we don't solve the derivative, we calculate it based on its current values, and then we project that forward. And at the end, we have discovered the solution through computational methods, right? Because generally speaking, yeah, that would be a nightmare.
Could dx dt depend on y? I mean, not dx dt, could the solution x depend on y from the y-ness equation?
Yeah, x and y both depend on each other, and they both depend on t. Right? Like this is the whole reason why we need computers, right? So up here we see that this thing dx dt depends on x, y, and t, right? You could, if you had really cool math skills, you might be able to like write x fully in terms of t. But given what the solution was, do you mind just scrolling down? Right? Like, I don't know. That definitely doesn't look like it's solvable. That's not a known function to me personally, So one of these is x and one of these is y, right? And so there's some nice oscillations that probably comes from something having to do with sine of t. But I don't think that it's meaningful in this class to try to get to the underlying analytical solution. What we want is we want to train the rocks to give you the solution. Yeah.
You go up a little bit, please.
You don't talk to me. I'm not in church.
Oh, sorry. So I see that you have R equals array, and then you have your brackets 1.0 and 1.0, but above it, you have an array that's f of x and f of y. Why wouldn't you just put f of x and f of y in the same spot?
So this array R is gonna be our values of X and our values of Y. But this array is gonna be our like our output values from f of x and f of y. So right here, x is R0. That's coming from right here, because we're telling it that your first value of x is gonna be, or the 0th value of this array is gonna be your x. The first element is gonna be your y. And then if we do the for loop, through the for loop, we'll get new values of R and for x and y. And we're telling it that for every new value, go through this, do this, and then give me the answer, the answer in this.
So that's like 99.9% perfect. So I don't want you to distract from that. It's a very good answer. Okay. So basically the idea, if you scroll down, right? So what he's saying, wait, a little bit farther, sorry. What he's saying is exactly right, right? So we start with these values and then we use this updating function, essentially. You hand it your current XY and you get out the new XY. The only tiny thing that I want to note is that you do have to multiply by H here, right? So the thing you get out is not exactly X, but really like V of X or the derivative of X. And then when you multiply it by the H, then you get your new step, right? So this is the next step, next step, next step, next step, using different combinations. And then you actually improve your calculation by taking this funny sum, right? What we call a weighted sum. It cares more about K2 and K3, and K1 and K4 are what we call correction terms. And believe it or not, you know, we went from Euler to RK2 to RK4. You can keep going. And you'll have more terms. And you'll have more correction terms. And the sum will be weird. Okay? But the process is the same. Just like we had before. You hand it your current position. It gives you back what the new speed is, essentially.
The only thing, I think if I remember in this chapter, it said that this is probably going to be the most complicated part, since we've done before, we've done this already. But the problem is now that we're going to have to define more than one variable.
Yeah, that's exactly correct. Any other questions? Okay, don't close this because I do want to take advantage of this being up. Scroll to the top. Okay, so what do I like about this? Let's imagine that we're grading this work. Imports at the very top, good, right? So I might even call this section like, you know, import land, or someone said importations. I kind of liked that, you know, call this something, and like you always can copy and paste it. Okay, now what? What else do I like? Yeah.
Taking notes of like what's going on.
Yeah, there's little notes, right? So this is telling me at the beginning what's going on. It's telling me even at the very beginning how long the simulation is going to run. Good, so that's nice. Anything else I like? Yeah.
The next thing is the user-defined functions.
Good, and it's in its own box. You can certainly put it in this box, but because we're about to do this over and over and over and over, I want you to memorize this structure. You import once, and it comes at the top. Then all of your user-defined functions. That way, all you have to do is look for which one you're using that day and just click that one. You don't have to click giant, huge pieces of code, right? If you want, of course, you can comment out lines or comment out blocks. That's perfectly okay, right? But you should make it really easy for you to use your own code. Otherwise, you won't reuse it. And from now on, once you've built the wheel, you don't reinvent the wheel every single time you get up, right? The only thing that you have to do, what we're learning today, is you just gotta switch these out. And you can do anything you want on a computer? What the fuck? Like, that's so powerful, right? So from here, you can simulate, you know, a rocket going to the moon. From this part, I'll show you that later. Okay, does that make sense? Okay, so what else do I like? Go ahead.
Just the side comments, like for R.
Like,
Say,
take your-
remember R.
Yeah, little note to yourself, right? And maybe that was a note from him to you, but like, you might write that to yourself as though you're presenting it to someone who's reading it. Right? To demonstrate that you understand it to me. Okay. This is nice too. These are all your constants. These are not going to change in the course. So if you want to make some correction, you can do that here, right? And it's in its own box. Next one. You could, hold on, scroll up. You could combine these, right? This is fine to have two. This one in its own box and this one in its own box, I think we're getting a little too much, okay? So again, it's kind of an art form. I like that these are the same because we're probably going to use these multiple times, but you might not use this in the same way. You won't really know where these boxes end until you start to do it a bunch of times, right? If you start saying, oh, I always use this, I'm going to sort of upgrade that to live with this group, that's perfectly fine, right? And if this is the stuff that you want to change, or there's some constants in here that are changing from example to example, you can put that in there too. Next. I would say that this box deserves its own like comment and like fanfare, right? There should be a banner announcing its success, right? This is the engine. This is what you'll use for the next like 6 weeks. So you need to understand every single dot line piece of this code. Because once you get to RK4, you don't get smarter than RK4. We're not gonna, we could go to RK8, but returning, for this class, it doesn't matter, right? So this is what we'll use. And so you need to understand it in really good detail. Oh, good. And then, of course, the most important thing to me is that once you make the data is made here, by the way, do not put the plot in the same box as the data creation. Right now, how long did this take to run? Can you scroll up for a second? This took, oh, it wasn't run recently. Well, probably not long, probably like a second or two. Okay. When you're running something for 5 minutes, and you have your plot at the end, and you run it, and then you make a change to the plot, and now you have to wait 5 minutes to rerun it instead of just recoloring it, you've wasted your time. Okay. Anything else? Okay, thanks so much. Let me steal this back, and I'm going to check that today's pair programming is actually relevant to the class, or see whether or not I fucked up. So let's have a look. Does anyone have the book in front of them open to this problem? What is it? Oh yeah, this one's good. Okay, so this is a little bit of a recap, I guess. We're not going to use this one. So I'm debating whether or not we should just try to apply it right away and come back to 523. You should do 523. It's a really fun problem. Let me see what else is around really quickly. What does 8-2 look like? Yeah.
Walkable pair equation.
Yeah, let's do 8-2 right now. Because everyone likes to murder foxes and eat rabbits, right? Yes or no? Do you believe in the circle of life? Raise your hand if you believe in the circle of life. Okay. So we're going to simulate it. Remember how we talked about the fact that not all of our variables need to be spatial? Well, A will be a rabbit and B will be a fox. This is a very common predator-prey relationship. The dependent variable is, or sorry, the independent variable is time, because the system will evolve with time. So let's try this. I'm going to bet it doesn't take that long. And so instead of leaving, we'll sort of switch gears and we'll go to 523 after. and at least open it and have a look at it because it's a really cool problem. Okay. Comments, questions, concerns? What? You're gonna make the rocket. That's part of homework. Yeah, yeah. You're gonna shoot a rocket from here to the moon. Mars, one of the two. And if you want, you can simulate it for your final project. What? Okay. So let's not get ahead of ourselves. Let's understand how rabbits eat first. Go back to your groups and from Monday. And let's do this one, 8-2. And then we'll do 523 after. And if you have 5 minutes right now, send me a message on Slack about when you want your interview to be. Next week or Thursday. Do it online. We can do it in person.
Are you good tomorrow in person?
No, but I could be potentially.
You're making drive all of them.
I could do it. For you, I would do it.
Electricity.
I would have given you.
Yeah, well,
This means there's no homework if this is a 8.2, the homework was 8.2.
no, the homework's not 8.2.
Oh,
8.3.
I'm sorry.
No, 8.3 is the next one, and those are the Lorentz equations. It's very similar, except it's in 3D. So I think if you don't do 8.2, you're gonna feel a little out of place for 8.3. Are we missing some? Oh, no, no. Okay.
Yeah.